This is Juyang Weng. Welcome to the talk. The title of the tutorial is Emergent Universal Turing Machines in Developmental Networks, Vision, Audition, Natural Languages, APFGP, and Conscious AI. If you need more information, I would suggest you go to the website. There are some additional information there. The contents will cover autonomous mental development by robots and animals. That's related to the ICDL conference. Turing machines and universal Turing machines. Then developmental networks. The theory of developmental networks is the theoretical properties. It's optimal with limited resource. Then the next subject is how universal Turing machines emerge inside the DN. The next is APFGP in the title. It means autonomous mental development for general purposes. And talk about vision, audition, natural language understanding, the three bottleneck problems in AI. And finally, we talk about conscious AI and conscious machine learning. The first subject is AMD for robots and animals. AMD is the subject in the workshop supported by National Science Foundation and DARPA held at Michigan State University in the year 2000. Then 7 authors wrote a policy forum titled Autonomous Mental Development by Robots and Animals that appeared in Science 2001. Then we started a new direction called task non-specificity. Basically, a machine must be able to learn a series of open-ended tasks that's not limited in terms of the scope of task, typically from simple to more complex tasks. Then we have a genome-like developmental program called DN, Developmental Network, that's pretty short, about 2 pages long, but it's supposed to be general purpose for development. Then we have ICDL conferences. The first workshop is an ICDL-1, then we have a second in MIT, and so on. Then the IEEE Computational Intelligence Society started a technical committee, AMD Technical Committee. Then about, say, 9 years, actually, 9 years from the start of AMD direction, we have an IEEE transaction on AMD. Later, it's called, change the name to Cognitive Developmental System in order to attract more people, because people say AMD, the mental, not many people understand it. So we say Cognitive Developmental System. Then we have experimental systems, we have web networks from 1 to 9. And we have APFGP, and we was lately, say around 2 years ago, we have a conscious AI. Now, first talk about the tasks. There are many, many tasks the AI system can do. And many people thought that, oh, there are so many tasks, then I should write a program for a particular task. Now look at the variety of tasks that we can look into. Say vision-guided navigation, all right? May not just use laser, because laser has a lot of limitation, like distance, like the problem with dark surface and wet surface and water. Then audition, it's not just speech processing. You can talk about the recognition of sound, natural sound, and other natural sound, including speech. The natural language understanding, it's not just language processing, including acquisition of mother tongue. There are other issues too. And we have been mostly doing pattern recognition, actually. If you look at the, say, vision, audition, and natural language, they are mostly using pattern recognition techniques. But I will explain to you in this tutorial that AI is not just pattern recognition, and what do we mean by that, all right? So we have games, for example, and the games are clean problems. They are really not considered AI problem because clean. And look at the first example of task. Suppose we have a vision guided navigation for driverless cars. Then you have a pedestrian, you have cars, and you have check signs, you have shadows. So driving is a very, very challenging task. Even you have a range map, but actually, I don't think range map is going to lead us a reliable driverless cars in a city setting, or even in expressway, you may have a detour, you have construction going on. So the really the privacy direction is using vision, like video cameras. So we'll deal with that issues. Give a simple example that we have a driver or a work assistant. You have the real-time computation, you have object detection, and you need to decide which direction to go in the presence of many obstacles. And in the 2016 example, we use a single camera, and you use direction taught by a human using joysticks, and use a GPS system for long-term directions, but local directions, short-term direction may be inconsistent. So you are integrating long-term goal with the immediate goal with the presence of very complex visual scenes. Then you also have a parking. If you have driverless car, you have parking, and good example, how you find a spot. Then you have to get in and without cause collision and gets out. Talk about audition, you need to attend. For example, you have a cocktail party, you have maybe you'll pay attention to one speaker, but others are talking. So you maybe also need to integrate the lip reading and spiritual idle noise. And in terms of speech, typically, suppose you have a label. That label at the end, say in this case, phoneme, but you may have many, many frames. Each frame may be covered 20 milliseconds. But the issue is how you can enable the system to understand the context. If we just provide a label at the end, then the label is not sufficient to generate the context. And it's called dense actions. And we'll talk about that with the general framework. Another issue is natural language. In this example, we have English, French. Suppose I have a bilingual environment. Father, mother will speak English often, and another speak French. And how you acquire language, right? You may have a dialect, for example. You may have sign language. Actually, sign language is more complex than a text language. And you learn mother tongue. And you also need to learn, based on some individuals' experience, maybe as a second language. Now, in the example we will cover, the example here right now, it will be reviewed later on toward the end of the talk. Then we, I think the third section, third hour, we will talk about the experimental work. I just give you an overview of the general purpose nature and experimental result that will come up. And in this case, we have a bilingual environment, English and French, and we have 1,000 words. We have like 8,000 context. Then without noise, it can 0% error. And with noise, basically the pattern, you have noise, then you start to have a little bit of noise with errors, but the power of context is to make prediction. I will talk about in the third hour. And the next subject is about C. C is consciousness. And C is really has a degree. Even your baby time or toddler time, you have different degree of consciousness. And give example, that baby did not understand the PhD work, for example, and it learns through lifetime. So we should not consider consciousness as a thing, but rather a path along the path of development where skill of consciousness will be improved, acquired. And that's what I said, that you need to through lifetime APFGP in the sense that when you learn, you need to also program your action and your attention so that your skills is based on the skill you already acquired earlier. It's kind of cumulative, and that's what we call C, consciousness through lifelong APFGP. Now, in terms of the system, we need to talk about first modalities, sensing modality and motor modalities. The modality including, give example, particular mode in which something exists, experienced, and expressed. And in terms of sensing, you have vision, audition, touch, smell, taste. In terms of motor modality, we talk about the actions, so you can speak using your vocal tract and mouth, dance using the body, walk using your eyes and the legs, learn swim. Now the issue here first, do we need a body? And I think that human without body is very difficult to learn. Even with handicapped body, for example, learning is very much limited. So I think brain must learn from its body. So you interact with the environment, then you learn when interaction takes place. Review a little bit about the history of intelligence research. On this side is in natural intelligence, and this side artificial intelligence. And human intelligence has attracted so many scholars. From 500 BC, we have Socrates, Plato, Aristotle. In the 1500s, we have Leibniz, Locke, Descartes. In the 1800s, we have Pavlovians, we have Tom Dyke. In the 1900s, we have like Lumenhardt and J. McCullens. I just give you a few examples because these two people wrote up a 2-volume book, Distributed and Parallel Processing. And in terms of artificial intelligence, because we don't have computers too late, so 1900, Alan Turing wrote probably the first paper on artificial intelligence. So we consider artificial intelligence didn't start till 1900. Then because natural intelligence has developed for a very long time and AI came in 1900, And there is fragmentation going on. Natural intelligence is without computation, and it developed very much observing its humans' behaviors. And artificial intelligence, when come up with computers, with little neuroscience, because neuroscience is a pretty new subject with the improvement of imaging techniques. So we have fMRI, we have other devices, and AI has insufficient links with natural intelligence. Although we do have people, AI research talk about the cognitive science, talk about the psychology and neuroscience, but the linking is still relatively weak. The tutorial here tried to put a stronger link. It's not the end of the research, but a beginning of the link. And within AI, we have fragmentation. Different tasks are using very different techniques. And this tutorial will try to put a picture where you need a unified architecture methodology for all kinds of tasks. So instead of ad hoc for each task, but you should have very sophisticated techniques that's sufficient for all tasks that a system can learn. Now, I'll review a little bit the history of AI. Alan Turing, in 1936, wrote a paper about a model, what it's called, later on called Turing Machine. In that paper, he proposed something called imitation game, but it turned out that imitation game is a kind of misleading. Many people start to work on this imitation game. You know, only the kind of starting point for Alan Turing to propose. And in that paper, he talked about the neuroscience, even religions. Also, we are misled in some sense in terms of the Turing test. And in 1950, he had a paper, very influential paper, in which he raised can machine think, right? And then actually from that paper, we start AI, you have symbolic AI, and you have connections AI. In the 70s, 70 years after that, basically now, AI has been on a weak track. Basically, we always talk about almost all the paper I have read. If there are exceptions, let me know. And I note that traditionally there are some scholars who are talking about teaching a vision system, for example, but still many programming because the machine is supposed to learn a task and you just do a demonstration through supervised learning, and basically it's many programming for a specific task. A lot of task-specific information was already handcrafted. So that's a very bad, weak track, and I think that we should change. And the programming for a specific task, there's no strong future, right? The technique itself is weak. So we need to be rethink our way of approaching intelligence system. That's why in the 2018, and I wrote APFGP paper, and that was rejected by Science and Nature without surprise. And I submitted to ARXIV. And 2 years later, this year, I won't be able to publish conscious AI paper, and it was rejected again by Nature and Science. And I would thank AIXIV. They allow a paper to be submitted without much censorship on the content. Ever since AI was started, probably by Alan Turing, there are two schools, and they are very different in nature in the approach. The left column we see Symbolic School, the right column we see Connection School. Symbolic School, basically you need to define a symbol, that each symbol represents a concept for a particular task. So Minsky, he did both actually, but he criticized neural networks. He said that the symbolic system are logic and clean. And it's false logic because it's based on the logic that we humans are familiar with, based on what? The symbols. And symbol is handcrafted and defined by a programmer. And of course, humans understand the human language. But machine really did not understand the symbol at all. So it's clean, but machine is really, really in a dark, total darkness about what do you mean by symbol. Right? Even data is fed later on, machine had no idea what to learn. And in the 2000s, we have been very rich in terms of common sense knowledge base, but somehow that the knowledge was based on human crafted representation, and this kind of database or knowledge base are very difficult to use by practitioners. And in the 2020s, this year, and I think that we need to be thinking about the limitation of Symbolic School, although Symbolic School has been doing a lot of work and improve our understanding of the issues. On the right column, we have Connection School, almost from the same year from Alan Turing's paper. And it's analogical because it's about a neural-like computation. It's a numerical processors. It's indeed, as Minsky wrote, it's a scruffy because numbers are not really related to the symbol on the left column. But it does sensory processing like pixels and muscles. I will talk about later, all right? So it's very different in terms of the definition of the symbol. Over here, we have pixels and muscles. Then we have neural networks, we have CNN and deep learning, and I will talk about the why it's hard right now. And I like to alert you that there is a huge problem of frauds going on, and deep in terms of fraud in the techniques that we have been familiar with and many people have been using. Now I propose, maybe I propose to you to consider whether we can unify the Symbolic School and the Connection School under the framework of APFGP. So everything has to be automatically programmed in a task-done specific way. Then we will be able to understand the limitation of both schools. And we want to take the best from the two words. An example of the Connection School here is that for letter E, you have a A1H, A12, A3, we have a B1, B2, and with some tolerance, then you do a statistics learning, but those age segments already predefined. Use this example because the pattern recognition by KS4 has been well known. And in terms of the Symbolic School, you define symbols. They are handcrafted, static, and task specific. Example, we said those are the ages for letter E. But there are other symbols, and depends on the issues, they may also define as a symbol. For example, task, goals, purposes, context, roles, and features. And they're brittle because the symbols are handcrafted by the human being. And if the setting go beyond the symbols defined, then the system breaks, all right? But deeper problem I'd like to call your attention is what they call PSUTS flaw. It's controversial, and I raise that issue, and many people probably don't like that, but this is academic discussion, and let's think about it, and let's discuss that. So the PSUTS is a post-selection using test set. Basically, for Symbolic School, you know the micro word. You know what kind of test settings they will apply to, and human look at test set. Then you design the presentation, in this case, symbols. Then it's really based on test set. And the system is not able to go beyond the test set you already envisioned as a micro word, all right? Maybe it's not like that. Maybe you need to go beyond your home, right? Go into other room, go into street, and go into school. And the neural network is slightly better. I would say slightly better in the sense that I did not define this rigid simple in a symbolic way, but still have fixed symbols. For example, in the Neocognitron by Kunihiko Fukushima, I use his example because he used a network that's a deep cascade, and he has a fixed interconnections, and he have available connections here. And the flawed part, I would say the PSUTS part, is to select features based on human know what kind of test set you will provide, and human manually select features in the network. Certain parts are adaptive, like those kind of arrows, but this part is static, human selected. And I propose to you to consider whether it's a fraud. And the connection school handcraft symbols in terms of the human selected features, all right? Static, task specific, and also static on symbols. For example, that you have a task to start with for a particular neural network, all right? And sometimes you select the features, those are the features and context, and you may select the rules. And a neural network system also have many super parameters need to be selected or searched for. Is that less brittle than the symbolic school? And many people argue that. And I think that in some sense that's true, all right? Because it does have a lot more parameter to tune using data set, but they still suffer PSUTS. There are two types, human and machine. I will talk about that later, all right? What do I mean by human PSUTS and machine PSUTS? Now, limitation connection school is that currently many neural network I read about using open skull approach, human intervention into neural network. For example, that you select the features or you do a search, when the search of the system parameters based on test set, right? And there is post-selection, use the test set like a training set. Basically, you look at the test set you may have, or you may be even envision, or look at the result of the performance. Then you start to tune the parameters, or you select features, or you do grid search, or use random weights to pick the best network. I will talk about it. And typically report the best network, or acceptable, or average or best using a test set. Now, the APFGP I propose here is a new paradigm, autonomous programming for general purposes. And inside skull must be totally closed. Inside the skull must be fully autonomous. So you cannot, after the birth, you cannot fiddling the techniques and the parameters inside, whether it's random weights or hyper super parameter. And that's a through life. And outside scope, for example, in nature, for example, you have a blackboard or you have a physical process. In nature as a teacher, including humans, and open-ended tasks, and tasks must be open-ended. And typically for humans, from simple to complex tasks, the parents and the teacher will teach. And you need to share skills across tasks. And there's no reset signals between tasks. If you want to say, hey, we don't have a, like lesson 1 and lesson 2, I have a reset signal button or a particular switch to take, this is the border between the task 1 and task 2. And that's a lot of information there. And a signal must be shared by many, many tasks. And the learner must automatically figure out what you mean by task, all right? History of deep learning, we have Paul Weber's has APFGP. Then we have Fukushima neocognition. And Fukushima did not use APFGP because he hand-clipped select feature, and a certain part of the adaptive part is based on clustering. And when Huijia and Huang in 1991 started Perceptron, it's the first deep learning for 3D word, and have 7 new ideas. And I think that the organizer of ImageNet learned ideas from the early work. It's not very popular, but I allege that data falsification and also the organizer mislead the public by making claims to exceed human performance. And after that, Google funded 400 million to DeepMind. And suddenly, because of the amount of money involved, and deep learning becomes super hard. But I allege that that Google was misled, and the senior administrations was misled by plagiarism and fraud. And I'll talk about that later. Now, what do you mean by plagiarism? Plagiarism, by definition, is the use of the published idea and pass on as your own without proper citation and credit to others. And is this particular diagram shows that the color one is IP. The color as particular is IP. And if you have a solid line, it's intellectual property, it's a block. And if you have dashed line, then it's alleged fraud. And marked, if it's masked like here, means that it didn't do this technology. Enable means enabling technology. And over here means that you, this particular work plagiarized the inventor. This is the label for inventor. All right, this is the name of the IP. So what happened is Paul Weber's the APFGP and Fukushima had the neocognition, but skull open. The skull open part is a fraud, I think. If you think of the PSUTS, but it's a human selection. Then Perceptron had 1, 2, 3, 4, 5, 6, 7, 8. So 8 IPs built on Fukushima's idea of cascade. Then Lagom, Purdue, Fei Li, Purdue 2000 is HMax, sorry. Then 2011, there is DN, later on doing APFGP and conscious AI. Because they are so integrated, I will not treat it as integrate individual building blocks. And I don't know even the height, so don't know how high that is. But later on, we have a Hinton, that's from ImageNet competition, and this is plagiarism. and the color corresponding to this, for example, that corresponding to this is corresponding to this is corresponding to this is corresponding to that, and this is corresponding to that. And Google got into AI. I'd like to congratulate, but probably the researchers at Google was not familiar with the history, and they started to plagiarism and fraud. Dashed. This is fraud, actually. The error backprop is a fraud. I will talk more about it later on. And the mass pad is plagiarism. That's an overview. Then just an overview of the 7 ideas. When actually you go back here, there's 1, 2, 3, 4, 5, 6, 7, 8. But over here, I only list the 7. It's the first for 3D, and then the first for detection recognition, and with scales and stride scanning, and the first for large scale 3D object, because you cannot match large pattern directly. You need to have a deep hierarchy. Fukushima did multiple matching, but not a systematic. It's not automatic. It's a manual selection features. And for number 4, it does feature matching and subsampling automatically through cascade. And Fukushima select the number neuron by hand. And do position blurring, it's a weighted sum. And does max pooling, and many people cite perception for max pooling, but did not cite the other 6 new ideas. And perception was also first to do a post analysis into segmentation. It's not bounding box, it's a polygon. And there are many celebrating in AI deep learning, and I think that in some sense that plagiarize perception. And I cite Fukushima with my co-authors, and that's 3 publications: IJCNN, ICCV, and IJCV, International Journal of Computer Vision, International Conference on Computer Vision, International Joint Conference on Neural Networks. These 3 very, very respected conference and journals, and it's unlikely that I have not read about it. And further, it's unlikely that I have these ideas put together, and you really need to really put things together in order to have a confidence to approach these ideas. So the red names here, I think there are controversial over this work. Ian Lacombe, Joshua Benjo, Thomas Pajo, Li Feifei, Ian Lacombe, Andrew Yin, Jeffrey Hinton, and Google staffs along with Li Feifei. Now move on to the fraud. What do you mean by fraud? Post-selection using test set, because test set are supposed to be there, you are not supposed to even pick it. And I think that the some AI textbook also mentioned it, test set, you cannot pick it. Just like you cannot pick your exams. And there are 2 types of fraud, human PSUTS and machine PSUTS. And Symbolic AI and many neural networks using human PSUTS, given up you manually select the features because you know what the test set will be. And you know what expected, then you pick up the features. In fact, you cannot do human feature selections, all right? So that's even true for neural networks. For example, you select parameters based on tasks you already know. It must be task non-specific. And a machine PSUTS is like you do a grid search on the random weights or the super parameters of the system, like regularization terms. And almost all the neural networks they have heard about, SOM, CNN, recurrent neural networks, supportive vector machine, LTSM, and so on. And I list quite a few well-known work, not exhaustive, and I missed many. And perceptron and DN are the only neural network I was aware of so far that does not do PSUTS, and all others does, either does human type or machine type. And so to do some details, and why do we say the open skull is PSUTS? And open skull means that human interact with a hidden neuron and pick up features. And that's Fukushima Cognitron and HMAX, Leafy Face Network, LSTM, SOM, SVM, so on. And another type of PSUTS is to use random weights. And many people say, oh, I only search 20 sets. And many people use that more. Maybe they claim. But embedding that search into this, actually, the grid searched super parameter of human architectures, because each architecture will have a random weights of the neural network. So at least two types. One is random weights, another is a super parameter of the network architecture. So we have Hinden, Lacombe, Benjamin, Alphabet, and other network. And how to avoid both? You must skull closed. You closed your skull, it will not allow you to have interaction before the test set was collected and designed by somebody else, maybe. And you must use only one network. You cannot just search how many weights, set, and parameters. You must add one network. If you do really need to do adaptation, you must be fully automatic, all right? So perceptron satisfies that. All the errors of perceptron is recorded through lifetime, because perceptron is incremental through lifetime. And the DM does the same. But DM is optimal. Perceptron is not optimal, because perceptron is doing Hibbein type learning, doing incremental clustering. And from that, DM resolve the problem of the number neuron by doing optimal through maximum likelihood. And Turing Award 2018, and I think that I claim that falsified data. And one example, I show the difference, all right? Give example that in 2016 CVPI workshop, this is through the data, training network, through the SIMNet data set, this is 10 epochs, goes through the same network 10 times. And because DM is already optimized, and the review of the network, the data set will not really improve much. But the CNN, the best network we found, it's going very slow, very slow. This is like 100. This is a 10 epochs right there. Epoch. If you look down further, you will see grow down very, very slow, very slow. And even at that one, still not far from that. So this is like a 60% higher, or maybe like that. So the single DNA is always optimal in maximum likelihood. But the luckiest that CNN from post-selection from many, still far from the performance. All right, move on to the next subject, Turing machine and universal Turing machine. And I will be able to only review it, all right? I'll give you the concept. I will not get much to the detail because the automata theory is very extensive and very useful for AI systems. And I talk about the finite automata in electrical engineering called finite state machine. Allow left to right scan. If you have input, allow right to then will not really allow you to come back, all right? And finite memory for states. And a push down automata PDA, there is a working memory called a stack, but input you still allow left to right. You will not be able to come back. in scheme. And there is a last in, first out stack. And I'll talk about that later with that figure. There's a linear bounded automata. It's a restricted Turing machine. And we'll talk about it with a finite tape length. Left, right has a bound. You cannot go beyond this bound. They have a Turing machine and allow one-step scan of the reading right head and allow writing onto the tape. So just overview says that this is left-right scan. That's left-right scan with a working memory as a stack. And this is like Turing machine restricted. And this is a Turing machine. And all are symbolic. All are symbolic. Okay, let's go to each. Suppose I have a FA. And you design A, B, C, D, E in this case, that each state corresponding to a symbol and means a context, right? And the input is a little A, B, C, D, and only allow left-right scan, as I said, a finite memory in the state and a finite number of states, right? And you need to handcraft it. Over here, the output is acceptance and rejection. Rejection means that I have not accepted, and double circle means I accepted this one, right? And this particular FA is to accept all the strings that end up with ABB, all right? And PDA is adding a stack. This is input, you scan from left to right only, and is a stack. Stack means last in, first out. And that's the added functionality, but still restricted, but still based on the symbolic model. And a linear bounded automata, it's like Turing machine, I will talk about it, has a read-write head, but there is a bound on the head cannot go beyond that symbol and go beyond that one. So like TM, but finite tape length, I'd rather move on to Turing machine so they can see a Turing machine did not have the right end, all right? So Turing machine is weak in terms of the symbolic, all right? Symbol is very, very fundamental limitation. And it did not have internal representation in the sense that I will talk about internal representation in the skull, all right? And there is a tape. That tape is starting from left end, but there is infinite here, all right? So if you have limit here, then become linear bounded machine. And Turing machine didn't, but it can scan from left to right. So basically you can have a scan that corresponding to attention, but not the same. It's like attention, because read-write head can pay attention each symbol at a time. You don't really need to read everything, and just one symbol at a time. And allow you to sense, means read. Allow you to act, means write back onto tape, but only one letter at a time. And it has a context, right? Context right there. This context is like FA. And relate that one to FA later on, all right? So Turing machine, although it's very simple, have only three entities. Infinite tape, read-write head, and a finite control with state. It becomes what we know of computer industry, right? And a Turing machine, graphically, you start with a known test. The regular Turing machine start with known test. Then you write a program, and with controls and execute a test. Input there, and after done it, output there, all right? And there is a transition function, start with a state, then your tape symbol you read. This is space of the state, space of tape symbol, and space of next state, and the space of tape symbol, and the head motion, and right, left, and stationary. So that's a transition function of a Turing machine. So you can see the Turing machine has called 5 tuple. 1, 2, 3, 4, 5. 5 tuple is the language that it's learned by a Turing machine. And based on this theory, we have 4 types of machine now. We have machine in terms of the FA, PDA, linear bounded automata, LBA, in Turing Machine. In terms of grammar, there is a computer language you need to like program, right? It's governed by computer language. That language is governed by the grammar. And we have regular grammar, context-free grammar, context-sensitive grammar, and phrase structure. And phrase structure is still not the natural language because it's limited by symbols there. And the language type is called regular language, context-free language, context-sensitive language, and recursive enumerable. And those kind of languages said you can see their relationship. This is the most restrictive, and context-free is less restrictive, context-sensitive less restrictive, and recursive enumerable is more general, but still not a natural language, right? So the entire hierarchy, we call the Tom's hierarchy, is limited by fundamental symbolic formulation. I will get to that later on. You will see why it's a symbolic formulation. It's bad. There are a variation of a Turing tapes. Given example, you can have a double infinite. Given example, this type, this end is also infinite, and this is infinite. And we may have multiple type tapes, and they're all equivalent. And why it's equivalent? Put the nutshell is because they are all symbol. You combine different symbols together, you can define new symbol. So it's still a symbol. Now move on to an exciting subject that's very useful for our APFGP. It's universal Turing machine. The idea is very beautiful, but the tools are limited, all right? So this is a regular Turing machine. You start with known task, then you design the set of symbols, and you design a Turing machine transition function for this particular task. So we call it special purpose for a given known task. Universal Turing machine is exciting in the sense that the input tape does not just contain the data for a particular task, but it has two parts. As a program for a particular task, and the data that you apply the program to. So it's the human that write a program for the task he's interested in. And this guy write a general purpose computer control. And what it does is simulate a computer language is a 5-tuple Turing machine language that can simulate any program written by a user. And as long as you understand the 5-tuple language, Turing machine language, then this is a general purpose computer that can really simulate it. So it becomes general purpose computer. Then down of computer industry occurred. We have thriving industry and still growing strong. It's called universal Turing machine. Remember, where the task is from. The task is from a computer user, not from the designer of the UTM. So what about the brain? Let's look at the brain. All right? Brain, we have a gene. Gene is right there. We human design the gene. And how brain is a general purpose? Because we have natural word outside. We have humans, we have natural word that give us new tasks on the fly. Then our brain keep learning it. I repeat again, it's very important, all right? So general purpose machine, like brain, not Turing machine. Learn the idea from Turing machine, universal Turing machine, UTM, by considering the task is from the environment. You don't have tasks to start with, so you do not have without known tasks at all. That's how you can be open-ended, all right? Then you have general purpose computer. That's the revolution, there you go. APFGP borrowed the idea from UTM. It's a revolution. So I suggest you have a break one, all right? And let's have I would suggest that I will continue when I record, because I need to deliver my tutorial video today before I go to bed today. But I would suggest you probably go to the restroom and have a cup of coffee and water if you don't drink coffee, and have a break. Totally, we have totally about 3 hours, and we already passed about 55 minutes, and we have 2 more hours coming up. So I would suggest you have maybe 5 minutes break, and we continue on. All right. Okay, let's resume. You want to pause, you want to have a break, all right? And pause the video. Now let's resume the second part. Now, the subject is developmental network, DN for short. Now, we need to have some logic there. And Marvin Minsky criticized that network is graphy, is analogical. There's no logic. But now we said, no. Unfortunately, Marvin Minsky passed away, and I was sending his paper, and he was excited. John sent me the paper. I was sending him a perception, and unfortunately, he passed away a couple of years ago, and didn't see the excitement of merging the two schools, convergence of two schools, Symbolic School and Connectionist School. All right, so let's see, we need both the word, all right, the symbolic word and the connectionist word, FA, symbolic word, right? And we go beyond, we can agent FA before the state is internal. And you have output is basically yes or no. Yes means accepted, no means rejected. And we output state each time. Say, why do you want output state? Because the meaning, the state is very rich. So we call agent FA. And then in the traditional definition of FA, you have action output. Action output is for a particular task. So it's like attachment to a state. But we need to output the entire state, all right? And the states are everything. Right? Because it has action, has also tasks and context, all the things, and should not have state that's inside, all right? So they become agent FA. What do you mean by agent? Agent is something sense and act, all right? So FA need to sense and act. The action should be very rich, that's a state. Then with the control of Turing Machine is an FA. That's new. And what do we mean that it's control of Turing Machine FA? Suppose you have a finite control. And I have some initial reviewer, and he did not really understand. He said finite memory is a finite state machine. No, finite memory is not finite state machine, all right? Give example, I have a computer. Computer has a finite memory. A computer is a FA? No. I was really surprised that he was talking about that. He said, all right, so control of a Turing machine is FA because hierarchy, Chomsky hierarchy is set up there, all right? I go back again, all right, into back. And hierarchy of a Turing machine, look at that one, all right? So FA is a controller for the FA, for the regular machine. And the Turing machine is a controller because of enumeral language. Oh, how can you say that finite memory of Turing machine is FA? So the theory that I published means that the control of Turing machine is FA. So totally scrambled Chomsky hierarchy. So it's not what initial reviewer said that, oh, they are the same. No, they are not the same. And look at the Chomsky hierarchy, there are 4 levels. How can it be the same? So that's a revolutionary concept, all right? So basically that why the control Turing machine's FA, doing some manipulation. Let's say that this is a 5-tuple state, tape symbol, new state, written tape symbol, and head motion. We define that one, the gamma, that one is sigma prime. Then we put the entire thing here as Q prime, new state. Why do we do this? Because we want to output state. So this is Q prime. And this Q prime is bigger. And it's a still symbol because you have 3 tuples put together still symbol. Multiple symbol combined together still symbol. Then there is a little bit of problem because this Q prime is larger than Q. Do you see that? So it didn't fit Turing FA very well, but doesn't matter, all right? You still can write that way. The transition function of new machine, which is in the form of FA, is that Q is just one component of Q prime, all right? So basically, it's a Q prime with a lot of don't care components. So Q prime cross sigma prime map to Q prime, where the Q prime here has a lot of don't care. So it's a FA. It's a FA lookup table, but it has a lot of don't care components in the Q, basically. So we approved in 2015 that the control of a Turing machine is FA. I think it's a revolution. It's a revolution. And this journal, International Journal on Intelligent Systems, and it's an International Joint Conference on Neural Networks. Then look at why FA is bad. Even FA is a controller of Turing machine, and why it's bad because it's static, right? Constraint. Typically, there are many possible state symbolic. Human tries to prove many states to make it small, all right? Turing machine should be as small as possible, but the goal is already known because you know you want to do either a regular Turing machine or UTM. UTM is a special purpose in the sense that you don't have tasks. You really need another person to write a program in the language of universal Turing machine. And each program written by the user still a special purpose, like a computer program, all right? It's not general purpose. And different program cannot share the skill together. Suppose I have a John and Amy, they write 2 programs, they will not be able to share, all right? And a problem in the micro word can be a group G. So the G is already static. It's a micro word. It cannot be everywhere. It's a micro word, assumed static. And FA is a solution to the problem. You write a program as a Turing machine, and it's a solution to the problem human handcrafted for a particular task. Then the search algorithm is typically using a lookup table, all right? And if it's complex, you probably want to do better than use a Dijkstra algorithm or A-star search. A-star search has lookup, look at this feature cost, estimated cost, and Dijkstra did not have lookup, did not have look ahead, all right? If you're not familiar with this concept, you probably just pick up AI textbook, like Norvik, all right? Then from this point, I want to really get into a little bit of mathematical content, because without that, we'll not be able to really understand the beauty, right? And as we said that before, we talked about symbols. Now we don't talk about symbols, we talk about numbers. The numbers are components of vectors, and vectors are like images, like muscles, all right? And the meanings are in the images, in the muscles, but each vector, like image or muscle, does not uniquely correspond to a meaning, all right? It's just one sample of many, many images, one sample vectors of many, many vectors. And in order to do vectors, we need to talk about what we call principal component analysis. Many people probably are familiar with that, all right? And it goes like this. suppose I have 2D, I have 2 pixels, and each plus here is a sample. And if we model the data clusters, not necessarily by ellipse, and if I model the data cluster by 2 statistics, right? The 0 order is the mean of the vector, which is the center here. And the variance, 2nd order statistics, which is the variance or covariation. Then you are talking about ellipse, all right? In terms of fig, it's ellipse. You may have a series of structures, the people say the mixed Gaussian model. So basically you have several ellipse, all right? Several ellipse there. And in this case, suppose with the PCA means that you have a long axis ellipses and a 2nd axis shorter, and so those are the variance, all right, variation along this direction. According to ellipse, this must be orthogonal, all right? That orthogonal is called principal component. Then this vector is the first principal component because the variance of the data project onto this axis is higher variance, which is longer, and this is the 2nd principal component vector, and that's the 2nd variance, it's a shorter, all right? If they are the same, for example, they have a circle or sphere, and there are special cases where eigenvalue of the covariance or variance are the same, basically. Right? Then we want to compute from data points the variance and the vectors automatically without the covariance matrix. That's a very difficult issue, but turns out if you look into the property, it's not big deal actually. It's not big deal. So let's look into that. And this is called CCI PCA algorithm that published early on, and C for covariance free candid. Candid, we do not lose the variance information. And I for incremental, CCI incremental PCA. So basically you come up with this vector comes in, V of V1, V2 are those plus coming in. And you want to compute the eigenvector and eigenvalue. If you know the covariance matrix of those V's, the covariance matrix will have eigenvalue and eigenvector. But we want to have that covariance matrix. It's too big. All right, brain cannot have covariance matrix of an image you see on your retina, never. So you want to compute eigenvalue and eigenvector. Those are the features from data directly, from images directly without the covariance matrix. All right, suppose you have a 1,000 dimension V, all right? Covariance matrix 1 million, not possible. We cannot use that covariance matrix. So what it does is basically doing incremental computation, but optimal. So vector coming in, you compute mean vector, all right, it's a mean vector. You do computation of mean vector incrementally. This is the old mean vector, this is the new mean vector, and the new sample comes in, and the weight is computed automatically. And this one is the learning rate, the retention rate. Then you compute the scatter. Scatter, this is the scatter of this is the mean and away from mean and the scatter of the vector. You compute U is vector. This is the scatter for the first eigenvalue, all right? Then you normalize the incrementally computed eigenvector. Then this is the new scatter vector. You do inner product, you get response. Then response weight its input, learning rate, retention rate, learning rate, retention rate, if add together is always equal to 1. This is the, if without mu, the mu is called amnestic parameters. If U equal to 0 for all the T's, then you have straight average, right? Like here. If you do like here, and without mu, then you can compute that this is straight average of all the X. You end up with average X bar. And now you have a missed learning rate, and mu is not 0, then you basically put more weight to the new data because the nonlinear issues and street average is not best what you want because old data was based on the bad, not very good eigenvalue and eigenvectors. So you want to give more weight. Given up the mu equal to 2 means that you give the weight 3 times more weight for the data. And then you update it. This is called scatter vector for the next component, all right, next principal component. And you want to basically, you want to get also the component from V actually. So this is a projection onto the next vectors, then you get the difference. Then this vector is orthogonal to all the V's, all the early V's, all right? And then this one will be next V. Next V will be I plus 1, that's orthogonal to V. So keep doing that. So this is called residue. That residue is orthogonal to all the V's you already computed. And that will next one. So next V, I plus 1 will be orthogonal to that. And you keep doing that, then very quickly you end up with a principal component. And I don't have time to show the data. And if you're interested, you read the paper. All right, CCI-PCA is published in PEMI. Then we want to do loop component analysis because orthogonality is artificial. And the neuron didn't care orthogonality. So the algorithm is similar to LCA, but giving away the orthogonality, all right? So suppose I have a vector here, each neuron has a 3-dimensional vector, and it's instead of a PCA, we want to lobe. And what the lobe? Suppose I have a 3-dimensional vector, 3 pixels, and I have this plus, the image comes in, and I draw in a very clear fashion that, hey, you have a cluster, you have 3 clusters, but in general, you don't know how many clusters, all right? So you need to use as many neurons you have to detect those clusters. Suppose in this case, you have this cluster, maybe you want to pick it up, all right? And over here, we have 3 clusters, and the loop component means that each vector is like a representative of all the vectors here. And this is another representative and another representative. And each representative is a feature vector and represent all the vectors here. And this is like district. R1 is district 1, R2 district 2, R3 district 3. And each district is represented by representative. And this is a positive next situation. This is only 2 dimension, then only positive, and then the district becomes like that. If you normalize the length of the vector, for example, then it becomes circle, all right? But ideas are similar. Basically, these vectors must compete, otherwise they will be similar. So must compete. In this case, competition based on inhibition from other neurons. If other neurons are firing, they can compete with you to suppress. Black means suppress you, make you less likely to fire. But there's no guarantee that these vectors, 3 vectors, all right? 3 vectors like V11, V12, V22, V23, and V31, V32, V33, they're orthogonal. There's no guarantee. So you can see that V1, V2, V3, they are not orthogonal. These 3 are not orthogonal either, but they are spreading out because they compete, all right? Once they compete, they don't clutter together. So the DN1 algorithm, in fact, is based on LCA, all right? And it has 3 areas. Input area has a sensory area X and a motor area Z. And also does input and output. And if you output X means predicted image, and output Z means predicted output of action. And Y is skull closed inside brain, all the neuron inside is hidden neuron. And for each time and each area, A could be X, Y, Z, and 3 area compute in parallel. And each network has a adaptive part, which has neuronal weights and age for G, and updates. And where V contain all the snap weights vector and G stored all the neuronal age. For example, use random weights vector for 0 ages and initial response, and for initialize the adaptive part, all right? And DN guarantee convergence, all right? And optimal, not just convergence. Convergence does not mean reality, it means the change gets smaller. It's optimal. And all the random weights means you get exactly the same result, all right? And you see why it's that. And it's a generative DM, and does like this. All right, so so you have time pass by, then every area perform mitosis equivalent if it's needed, and using the bottom-up, top-down weights, and the B for bottom-up, top-down. Then bottom-up, each area has bottom-up input, top-down input, and then this is the adaptive part. You compute a negative response, and you have also the update adaptive part. I will talk about area function next. Then you do weight for bottom-up in normalized vector, you do inner product, and top-down vector, you have weight and the top-down input, you do inner product. So you end up with 2 inner product of 2 unit vectors, and you have V for weights, and P for weights is V is normalized. So the maximum value is 2, minimum is -2, right? And because this is maximum 1, lowest -1, -1. And to simulate the competition, we do a top K. Basically, look at the pre-action potential, you pick the maximum, and win. Win the neuron will fire, all right? And then fire you update, all right? Learning rate, this is like PCA, but LCA right now. And we response weighted input, then this is the old weight, new weight. And then you update weights, all right? And this is the learning rates and this is the retention rates, right? And this is the hidden learning. And you can prove that the V becomes incremental average all the inputs actually, all right? Incremental average. So average is best for a certain type of distribution like exponential types or uniform distribution. So it's optimal, all right? And DN2 is different from DN1 in the sense that its motivation is DN1 use handcrafted hidden hierarchy, and the number of areas are decided by hand, and each area has a fixed neuronal resource, all right? And then inside each network area, it does inhibition. And that's bad because you want to have even the number area is fixed. You want to have internal structures that emerge, not just a fixed law of competition with each area. So inhibition zone for each area is adaptive. Each excited neuron in J has inhibited neuron in -J. Neuron IJ fires if and only if in -J does not fire. And neuron in -J uses hidden learning to connect competing neuron. It collects all the competitions. Then the neuron NJ finds the competition zone through its inhibitory neuron NJ. See that? Then inside each area, even the entire brain, you emerge a dynamic complex structure of the hierarchy because each neuron can find its own competition zone instead of DN1 where each area has its global competition. And then because you have a competition and we like to have XYZ, and you have also initial connection to be more effective. So we have X like this here, means 0 means no connection to X, 1 means connection to X. Here means 0 means no connection to Y. 1 means connection to Y. And 1 means a connection to Z. 0 means no connection to Z. Then we have, we don't have 0 because you need to connect somewhere. So you have 1 to 7, we have 7 types, connection type as the initial connection, so that the network will much faster to collect the inputs, and the rules are faster to find. Then the DN grows a brain because skull close in the brain area. Over here, we have explainable brain. It's explainable AI. It's highly recurrent because you can see that it goes down and up, goes down. It's highly recurrent. It's a no hope to hang program, I tell you. And I explained to you the beautiful logic, right? And A means that each neuron has 6 fields, right? Each neuron has this is a sensory receptive field. You have a sensory effective field. You have a motor effective field. You have motor receptive field. You have lateral receptive field. You have lateral effective field, 6 field, all right, for every neuron in general. Then pixel didn't have bottom up. Motor didn't have top down input, basically. And this is B. B means area will emerge, all right, emerge in occipital, temporal lobe, and parietal lobe. The motor, this is a frontal motor, and this is a ventral motor. And this is a very coarse description. Give example. Suppose that suppose I have an object A, and the red neuron will have receptive field, and for object B and blue neuron have receptive field corresponding to that. And if we have enough neurons, like here you have 3 neurons, and the feature will match this A well, but the other feature at the same location in the same column will match other feature for other object of the similar receptive field, but different features. And then you can see that you have a different receptive field. You have different types. Each receptive field have different types. And for type invariance, you need to collect all the same type neuron from different locations. That's how you have here. Oh, this is over here. You have type invariant, right? They have all the type, all the value we collected, and based on heavy learning. And this we have another type, blue type. See that? So all be connected. Here for the location, it's a type invariant. So you collected all the neuron of the different types from the same location. So you have a type invariance, you have location invariance. There are other invariants too, all right? And look at the TM. Suppose this is a TM because FA is a controller Turing Machine and a developmental network. And if you have a symbolic network like many DNN, it did not have a state, I tell you. Even you have reservoir computation, right? Because reservoir computation, it's hidden. You cannot talk, cannot teach the state. And we can teach a state here. Can teach state, then understand that we want to remember, okay, because it's highly recurrent, you must unfold in time. By unfolding time, then this is a time 0, 1, 2, 3. And then you have each column corresponding to time. Each column input, you can only use the input from the left column. So time T1, you can only use input from the left column. See that? And this is the motto. You have a pattern. Each neuron corresponding to a concept right now is what, where, scale, for example. Then these particular neurons that match this 3 concept pattern, and this neuron corresponding to different pattern, corresponding to different combination of concept. Then this is the bottom-up input, and bottom-up you have a global input, you can have a local input. See that? And each neuron corresponding to a particular weights for a feature of the receptive field, and also the locality of the bottom-up, and also top-down context. So this neuron is like an entry in the FA. And it do competition top one. And if top one, whatever the win, and we'll take that input, if it's random weight, the incremental learning will guarantee that you immediately take the input, all right? And they forget the random weights. Then we'll fire for the particular. Next time you have this input, you have this pattern, guarantees this is the top winner, because only one, this one with the best match, and response pre-action potential is maximum, which is 2. If we divide by 2, it becomes 1. And later we do 1 actually. All right, we normalized. And then once it fired, and if you have supervision at time T2, then all the black neuron will be linked to this one if it's the first time fire. And this pattern of one neuron firing or other neuron are not firing, this entire pattern will be learned by the corresponding firing neuron. And other white neurons not firing will not really learn. So it's a perfect logic. It's optimal in the sense that the connection of the weights here is a probability, all right? If you look at the proof, it's there. So basically for each input here, in terms of the input and in terms of context, you need one step here to fire in the hidden area. The next emerge the action. So you have 2 steps, 0, 1, 2, 2 steps to get out, all right? And that's a perfect. Next time, for example, that next time, suppose this is the best match, right? If you are looking at here, and that's the best match, mean that at that time, in this context, if this is matched context match best, you should look at local feature instead of global. Here's global, and here's global, and here's local. Then it fired, and we look at here, the global, and you go to next one is which is the type or location of the feature. Here is the context, right? For this context, you should look at this local. So attention is automatic. Now look at the example. Suppose you are to vision, all right? And vision has a lot of context. Look very complex, but simple for child and machine. Why? Because everything inside is automatic. But let's look how complex that is. For example, we have an action, all right? This is the GPS action, where to go, and where you want to teach the system to look at it, what object, all right? And those are the concepts, all right? That's right turn, slightly right, forward, right turn, left turn, and stop, and like that. And GPS has its own action. So your action may not be considered GPS. Then we have object types, all those things. And you have a scale, big and small, for example. And once you have this vector is in, and you have vector coming in, you have image coming in, and 1 step, 2 steps. And then next you do locally, see that? And this is on the fly, everything going on. So attention is automatic, and the feature is automatic. All you need in this particular supervised case, you need to supervise motor at the right time. But we'll talk about reinforcement learning later on, and everything here can be emergent, all right? And reinforcement learning will pick up the action or state that get rewarded, and suppress the action or state that's punished. Then the next issue is how you do segmentation. And suppose you have a background, right? If the receptive field is not really precise, then you are picking up the background, then you screwed up. In this situation, and we have, give example, suppose we have a cat in background, right? And this is the this is true object contour, and this length contour will not be perfect because the limited number of samples and a limited number of neurons. But you can see that how you can have a neuron that corresponding to this pattern, basically, and black means it's less weighted. Here's total back. Because we have synapse maintenance. I'll talk about synapse maintenance later on, basically. Suppose I start having receptive field here, right? And if I have a pattern, but I pattern this area matched well because it didn't change as soon as this object there at this location and I firing, but background changes, very important. If the background change, and like you see movie, right? I look at the object, the cat here, and the background change, and then the input here will not match very well. And you have large variation, and synaptic maintenance will cut input with large variation. And those will be automatically cut, and those material will be kept. So segmentation is done on each neuron, not globally, just like human. You know, human, if you want to do resegmentation, you do sequential decision. You want to say, hey, this is the edge, you know, and this is the contour like that. But for each neuron, segmentation is done for the particular neuron is automatic using what we call synaptic maintenance. And we use a function we call the synaptogenic factor that measure the relative match of goodness between the this is a good neuron and bad neuron, all right? And there's a factor we call synaptogenic factor. I don't think I will have time to cover synaptic maintenance. If you're interested, you probably should read the paper, all right? And how about invariance, right? The top part of vision is invariance, especially the skull is closed. In this case, you have location invariance, you have scale variance, which means how apparent size of the patterns, and viewing angle, sighting, you have 3D viewing angle, you have lighting condition difference, even though you have different lighting, same object will appear differently. And you need to also have attention, you have more than one object, even though each object you have an object hand and the toys here in this case, and you have background into the, pay attention to background or you disregard it. All those invariants, how to happen, it's attention, right? If you're interested, you read the paper. The framework here actually is sufficient to deal with all the invariants. How about relationship? In this case, you have object A, object B, and they are the same types of A-B group. You may have other relationship like A plays B, A gives B to C like that, all right? And then automatically build knowledge hierarchy. And how, I'll give you an example how it happens. So suppose I have object A, location A and B, and a type A and B. Then if I have other neuron that's more close to the motor neuron, and it start to have top-down input, and I unfold it so you can see it's have input really from motor. But in fact, the later feature is also in the Y area. All right, I unfold it out so you can see from left to right, but the network is recursive. All right, then you have this is called relation neuron, and you have a motor neuron that corresponding to group A and B. All right, group A and B. So they have relation. All right, it's everything's automatic. Now look at some experimental system we already have. We call earlier when we call it real-world networks, WWN, and from 1, 2, 3, 4, 5, 6, 7, and 9, and we have TXT, and also have basically take the pattern of the words as a pattern, so you can learn natural language. I will not be able to get into detail, but I encourage you to know that each version has a test on a particular mechanism. All right, move on to the theory part. Now you have an experimental outlook, right? You can use many tests, but what's the property? The property might be important to have a clear, explainable AI, all right? So we cover theory, theory with optimal, with limited resource. So then by 2015, in this particular paper, has several major theorems. Control Turing Machine is FA. And then DM can learn for any FA or Turing Machine use an emergent controller incrementally. And if you have sufficient neuron, this error-free, basically early neuron initialization is based on hidden neuron. So at that time, before all the hidden neuron are initialized, you always have sufficient neurons. So it's error-free, all right? Then after all the neurons have been initialized, then it's optimal in the sense of maximum likelihood. In other words, we do not have local minima issue, right? We don't need to do iteration. Believe it or not, read the paper. That's the beauty. And then emerge an optimal Turing machine. It's logically complete because Turing machine is logically complete if you talk about that logical Turing machine. And it also because that any Turing machine, as long as learned in a proper way, it's a universal Turing machine, right? If you learn language, for example, of Turing machine, then you can simulate any task, all right? So including universal Turing machine. And just a universal Turing machine not sufficient for autonomous learning because you must have a goal. And so in other words, in neuroscience called motivation. And in machine learning, sometimes we call it reinforcement, but reinforcement is just partial, all right? Emotion is a part of motivation. In neuroscience, it's called motivation system. Reinforcement is just a piece of story. And reinforcement is just a piece of story. So it should have a motivation system that include reinforcement learning, all right? Include pain avoidance and pleasure seeking. And I will talk a little more later on, all right, about our motivation system model. Then if you have a universal Turing machine from DM, what's missing? There are 8 properties that's required called Genesema. I call it Genesema because easier to remember because 8 is a little bit harder to remember. So basically we have G for grounded. You must use the physical word. You must learn from physical word. Simulation is useful for debugging, but it's not rich enough. Emergent representations. You must use an exclude emergent representation. You cannot have a concept about the word like handle of the door and put into neuron. Okay, cannot do this. And natural representation for M. And all the internal representation must be fully emergent. It's natural. You cannot have a partially emergent and partially handcrafted. Must use fully natural representation. Natural for the sensor means pixel, for example. For muscle means muscles for motor. You cannot have a particular symbol because if a symbol is fixed, then becomes damaging, all right? I for incremental, you cannot use batch learning, so forget about the image net, all right? Image net has a batch learning collected. It's very bad. Why it's bad? You will say, why it's bad? Without action generated, we will not be able to collect the next sensory input. So all the batch data is bad, all right? You want to use sensory recursive scenario so that if you don't turn left, you will not see left scene. If you don't turn right, you will not be able to see the right part, right? So you cannot collect the data without action. So all the statically collected data, like ImageNet, is fundamentally flawed. It's still go back to the pattern recognition. And the Genesema Turing machine is not pattern recognition. It's active. Actively search for data. Scope closed, you cannot, after birth, you cannot get into the network. And for motivated, emotion is a special case of motivations. You must do A is abstractive, not just fitting data. Right? Many neural net just fitting data. No. Must also abstract rules. How do you abstract rules? Turing machine concepts. So look at a little bit how you can do emergent data. Before you are symbolic Turing machine, even UTM, now you have a network, how you do it. So you have a Q for state, sigma for input, and you have a next Q, that's a FA symbol, FA symbol, that's a transition. And for vectors, you have Z to represent Q. Z becomes muscle vector. Sigma is symbol for input. Now you have X for image. All right, it's a huge monolithic image. Then map to the next state, and you map to the next muscle vector. All right, so the kind of vector to vector goes to the next vector. That's FA, emergent FA. For symbolic search, for neuronal competition, before you are doing symbolic search, this is a lookup table, just search the best match for the Q and sigma. Now we have to really do match of Z and X, right? We do competition. So we have many, many neurons. The neuron has weight Z and T. Z to match X, T to match, Z to match T, X to match B, all right? Then all the neurons have different T and B, top-down weights and bottom weights, and dot means normalized. Then you find a max of neuron IJ. I use IJ because you don't have the IJ, but suppose you have lookup table is IJ, then I still use IJ to match the symbolic lookup table. But in the brain, you don't have IJ. You just have a sequence of neuron, all right? And you find one neuron that's matched, it's the best match, then that neuron will fire, all right? IJ, I prime, J prime will fire, all right? And then you perfectly learn the FA if you learn incrementally, right? So DN is a control of a universe, Genesema Turing machine that learn each Turing machine perfectly if you have enough neurons. Theory 1, year 2020, we have a further theory 1. The control Turing machine is not only an agent FA, but also a tentative agent FA. We look at how the neuron can even take part of the X as attentive, top-down attention and bottom-up attention, right? And let's move on to the next subject, which is the universal Turing machine, right? Emerge inside the end, how that happens. So what's the minimal set of mechanism for APFGP? And that minimal set should be sufficient. Look at what the figure we already displayed from baby to adult, right? And for attentive agent FA, we may have attention to speakers, and as we showed earlier, for other speakers, and we lip reading and noise, all right? How we can do attention, right? And the minimal set over here, I propose to you, is Genesema Turing machine. All the 8 properties of the Genesemas are necessary, right? You cannot drop any. It's a minimal set. And you need a Turing machine, right? And for a procedure that can program self, all right? And you need the UTM because you need to learn the task, any task that you need to learn from the environment. So you must use the UTM formulation, all right? So you can learn any program. You learn any practically learnable task, each program corresponding to a task. But the entire Turing machine UTM is a grand UTM that shared all the tasks among many different programs because the neurons are shared, all right? Neurons are shared within the network. So let's look at a simplistic case. You see how internal representation are automatically generated without handcrafting, all right? So this is the FA, right? This is FA final automata. It's a symbolic. Basically, you have 1, 2, 3 as input, and you have state A, B, C, D. And if A, you have a 1, you go to B. B means accepting. And A with 0, you stay AA. That's a FA. And this is a well-known transition table. If you are majoring in computer science or electrical engineering or other discipline, as long as analytical, you know the state transition function. The ABC state, and this is only 0, 1, 2, 3, a symbol input. Then A with 0, you go to A, B with 1, you go to B. See that? A with 0, go to A, 1, B with B, 1, you go to B. And B with 2, you go to C. B with 2 input, you go to C. See that? So this is called transition table. For 4 states, 4 input, you need 4 times 4. How many? 16. All right. Typically, this is a lot, very big, and this is very big. Number of states very big, and number of inputs very big, and then this is huge. Neuron will do interpolation. I will talk about later. All right, and the symbols. That's why symbolic knowledge base is nightmare, because there are so many inputs. All right, and just too many. Now, we want to do emergent. You want to use vector, all right? So this is vector. I want to represent those states by muscles. So in this case, we have 2 muscles. And the input is symbols. We want to use pixels. Suppose by the image with 2 pixels. Then all the symbol here becomes numbers. And from that, it's harder for you to understand. Just look at the brain, right? Look at the pixel and the muscle, it's just hard to understand. But remember, that's FA, all right? FA, but just use pattern, all right? Now it becomes emergent. Why emergent exciting? Because the pixels emerge from the natural word, and the muscle also emerge. Muscle action is through trial and error or supervised by physical word or teacher, all right? So now this is emergent X and Z. This is the X and the Z. Now what's missing is Y. It did not have, I said that the FA of the Turing machine did not have internal input. Now we have internal input. All right, how do you do it? So DN wise adaptively, incrementally wiring inside the neuron is internal representation. All right. So all the symbolic network, you already know that do not have internal representation. Internal representation is from emergent weights, right? So Z is a muscle, first context, first input. And that one will be, this neuron will match the best, all right? So whatever the neuron, random weights happen to match best, will fire, all right? That particular Y neuron will fire. And that will be supervised by this one, the supervised 0, 1. And is this input 0, 0 and 0, 1, this is the, so this is the next stage. Suppose I'm dancing, I'm speaking. This is the muscles that will emerge, all right? Continuous motion, example, or supervised by physics, all right? Then this is the next input, and 0, 1 is the next state, and 1, 0 is the next input, that's the next one. So this pattern will be matched by another neuron in the Y area, and supervised by this one, all right? Now, you have internal representation this way, and this internal is this one, and keep going, and you always supervised by physical word, because physical word impose you, and keep doing that. So although the muscle are firing and the pixel are firing, and you have internal representation of the Y that has weights. That weights, you end up with a growing brain. Keep going. So the theorem 2 in year 2020 is by learning from any teaching Turing machine, regular or universal, through patterns with top 1 firing in the hidden area, the DN control enables the learner Genesema Turing machine to emerge inside it with the following properties. Before we have only Turing machine, now we have a universal Genesema Turing machine. Genesema Turing machine. Error-free, it's a sufficient neuron. Then you have error-free, you have insufficient neuron, it's still optimal. It's very different from early one. Early one, we talk about Turing machine. Now we talk about emergent Genesema universal Turing machine. And because universal Turing machine is the same as TM. Now move on to APFGP. Why emergent UTM? Because we want to do APFGP. Although human does APFGP when from the baby time, we did not think about that. For neuroscientists, they don't know programming, all right? Not much, but for computer science, we do many programming. And we did not really talk about APFGP, all right? Machine will not be able to do APFGP now, since changed. All right, so universal UTM, we discussed below, right? APFGP, we have autonomous programming for general purposes. You can think about automatic. Originally, I was thinking about automatic, but the term automatic is really like auto, car, you know? It's not really autonomous. So it's much better to be autonomous because programming by a brain or by you as a machine, you are really autonomous. You make decision on the fly, all right? It's not just like auto car, you know, you are driving by somebody else, right? Okay. So all natural intelligence use APFGP. That's a new perspective. Although it's obvious, but I have not heard anybody were talking about APFGP by animals or human, all right? Not in that term, all right? Although our computer scientists or students, they do programming all the time, but nobody said the brain is doing automatic programming. This is a person doing automatic programming. Makes sense? Then you have lifetime experience. You cannot do program day one. You really need to go to zygote, embryo, fetus, newborn, infancy, before you get admitted to computer science department of MSU, then you learn programming, right? So then you lose through the lifetime, your behavior become more and more low-like, all right? You'd like to make sense. Oh, this guy is a smart, all right? Becomes a 4.0 GPA student at MSU. And I have students that did not go to University of Michigan, Ann Arbor. They come to me, and although he was admitted by University of Michigan, Ann Arbor, he thinks that our work is more interesting to him. By the way, computer science department at MSU is slightly higher ranked compared to another university in Ann Arbor based on NIC ranking. I don't like ranking. I'm not a fan of ranking, but I just mentioned it so that for those who are rigid, very rigid, just ranking, even ranking, and we are doing well in this department. All right, the Theorem 3 on year 2020 said that a Genesema Turing machine inside DM automatically programmed for general purposes. And I still use automatic because it's interchangeable with autonomous for a number of purposes after it has learned a universal Turing machine and the related purposes. All right. So in other words, the tasks need to be learned. All right. The DM program itself is task independent and language independent. Why you say that? Because when we do that, we did not really mention a particular language. We did not really mention a task. All right. So if you're interested, read the paper. So now we have autonomous programming inside a network called DM, has two modes. Typically, in the earlier stage, you think about the learning from a teacher TM, right? And maybe for machine, you can supervise the actions. But later on, you want to have a machine to be really autonomous and let the physical world to teach it. So we have two modes, 1 and 2, but in the real situation, and these two modes are very much mixed, and they do occur in real time, and maybe certain effects are supervised. For example, if I shake hands, and then I supervise your hand in some sense, but your muscle of the vocal tract are very much autonomous. You say, Juyang, good morning. And that part is autonomous. And the hand is supervised by my hand, right? Now, then how DN can do autonomous programming for general purposes, and if you consider this is muscles, and this is pixels, and the same network we talk about it, it don't have to be the top 1, maybe top 3, top 10, top 10%. Then you have doing autonomous programming by DM, same DM, because you have physical grounding, and the network does APFGP. Still the same figure, that's beauty, that the figure you have seen, and still same, instead of DNA network now, we have a brain, artificial brain that does APFGP. And then the segmentation takes place, and it don't have to be restricted to like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Don't have to be limited this number of classes, because the action is muscles. Whatever the language of muscle specify the types or locations or purpose or task or intent. So the network has intent. Or the scale in this case, or the locations, and invariants, or relationships. How the network evolve through experience. Okay, now move on to subject of motivation. And I talked about motivation, and the motivation is extremely important. And some philosophers said that what computers cannot do, and what computers still cannot do. And I would like to answer him. Computers can do also emotions, as the intent. So motivation, we have excitatory connections. We have inhibited connections that corresponding to 2 classes of neurotransmitters, right? GABAergic, GABA, and excitatory neurotransmitters. There's quite a few. And in addition to these 2 types, we have 4 types. 5-HT, DA, SH, and NE. Let's see what that is. All right, serotonin, 5-HT. It typically means pain, stress, and punishment. So when you have punishment, and the serotonin will come out, right? That will have effect on the computation of areas, brain areas. And I would not be able to explain the detail of the papers. I would suggest you just read the papers about the motivation. We have quite a few, all right? And if you have like pleasure, like sex, then you get reward. For example, you have dopamine come out, and dopamine has an effect on neural computation. And for SEH, you have acetylcholine, and in our model, it's expect uncertainty. It estimate the variance, using estimate variance of the match of the inputs with the weight. And E, norepinephrine, it's novelty. measure the unexpected uncertainty. Then if novelty is too high, you may have novelty that you feel, it get aroused, for example. But for synaptic maintenance, this high means that you do not match well, all right? You may need to generate new neuron to take care of this case, and you need to cut the neuron that do not match very well, then you want to cut those matches, all right? And we are doing well to reach a breakthrough. And we spend 2 hours now, very good time. And I would suggest that you have a break and I will continue. And I plan to have a 3 hours continuous video recording so that we have a single file. And I suggest you have a pause. And the third part will be a lot of practical systems to use the theory we learned so far to apply to many, many complex tasks. And I will mention that. So when you come back, and we'll continue. And I will suggest you pause the video, and while you come back, resume. And where I will continue recording, all right? Now, the part 3, we do vision, then look at the kind of vision scenes. And the setup you saw it earlier, and in year 2020 came out in Neural Networks journal. We have 2 cameras. So general purposes, and the left eye, right eye integrated for stereo. And we don't do split matching left to right, Windows search, we don't do that actually. But I don't have time to talk about that, how to integration. It's very much a multi-sensory input. Left eye, right eye sensory, multi-sensory input. Then we have GPS as a long-term goal, all right, long-term goal. It's another sensory input in the motor actually. Then we have camera input is a local setting, what the setting look like. And we have automatic integration of multi-sensory input. And we learn the skills from experience, all right? And Juyang has a YouTube video, and if you're interested to watch the video, he has a real-time demonstration. And 1, 2, 3, 4, all right? The camera at the top, and you have a screen you show. Then you have joysticks that specify the action that the teacher teaches the system, and also has the input output in case you want to save the network and the load network. And it's real time, and everything is running on mobile phone. At that time, we did not have a powerful cell phone, but Juyang used the GPU version that become much, much faster, and the network then becomes really much bigger, allowed by the mobile phone. We have a high-end mobile phone and Sony. And the Sony has a 4K resolution, just 4K resolution, and then the resolution much better when you look at the images. A huge amount of variation. In this case, we have like tree shadows and a different like project from the light post. And we have same thing like other things. So we have different time of light, and we deal with those challenges automatically because you cannot just program that. And the one that we had shown earlier, right, look really complex, but now it's not. And I tell you what we saw before. It's just a vector, just a vector, and synaptic maintenance allow you to really pay attention to a certain part of vector, top down and bottom up, local view and local. Do you see that? And everything's automatic, right? And for this situation, we have sample data from AI machine learning 2016 data, and we collected monochrome images, and we have also actions, attentions, and that's published in 2019. And we we have a large data set, and we also have a like turning around. We have obstacles like that. And we have a MSU campus trend tested, but disjoint test in the sense that the section you use training is not the same as the section used for testing. And there's a blindfolded test where because the human has vision, right? If even the action from the system said that's wrong, you probably don't do it. So the teacher will blindfold himself. His girlfriend is watching, and that's another test called blindfold test, and both are successful. And in terms of the training and testing, and we have blue area, and for training, the red area for Weng neuron training, and the red time real-time testing. That's the extensive. You can see the disjoint. And I want to show you how the automatically general network allow you to disregard features that are not irrelevant. I call distractors. So basically, you may have edges like that, right? These edges are also edges, right? How the edges are those edges are not useful, but those edges may be useful because of statistics, right? So give example that you have this patch learned by this neuron, this patch in this neuron, and so on. And this higher neuron, which is a Y-type neuron, and that connection from top-down and lateral, and this lateral is from Y up, and bottom-up directly from this one. And this Y neuron is able to learn the combination, and based on that particular context. If I'm making left turn, for example, then I should disregard this kind of feature, this kind of feature. And so I automatically, if I turn right, for example, I will disregard this kind of features. So it depends on what you want to do. So the distractors are automatically disregarded. That's the first time there's context-based automatically disregarding features that are distractors. And this is more a feature look where give example that those are disregarded, these are disregarded, and those are picked it up because this is related to the direction. Statistically, it's consistent. So the important features and the irrelevant features. And those are irrelevant features, the important features. And those are response, all right? Those found response from early neurons. And then later neuron will group the output from those neurons. They have a deep quality, right? For detail, you want to read a paper of neural networks, 2019. And in terms of the stereo features, and we use color, each color corresponding to particular features. It's a pseudo color. And we have bottom-up weights and colors, lower neurons. And we have type 111, and those give you the visualization, what kind of features. And the meanings are attended complex image structures, all right? The meaning is embedded not only the bottom-up feature and top-down, but also the connection patterns. Now you want to ask the performance, right? And we train a different day and different time, and with a different neuronal type recorded, and number of samples are thousands, and we have how many actions corresponding to different segments, and we have 18 segment routes, and totally over thousands of time steps, and we have error counts about 0.7%. If you talk about the with ground truth, blindfolded do not have ground truth, because if I'm wrong here, you mean next time is correct. So the blindfolded test is like you fall into the outside the walkway, or you look into tree, for example. And that's the statistics. And totally 62 errors, time frames, count about, but those accounts are more The really error is 9 actually that lead to the navigation errors, but counts are 5%, but each frame count does not mean lead to error, basically. That's then embedded representation will embed our neuronal features into color, where the color over here is based on navigation action. Then the sequence are connected if they fired in time sequence. And you can see that the presentation kind of smooth. It's not like spaghetti going back and forth, but rather it's firing as continuous through neighboring neuron, all right? Because we do self organization, use LCA representation with synapse maintenance, and representation is kind of smooth, but does not mean that it don't have jumps. You want to say, how do we embedding, all right? So we find that the first 2 principal components of the weights, and we project that high dimension, highly 1,000 dimensions of neuronal weights onto the first 2 components space. That's how you end up with this. So jumping here did not mean that jumping very much in 3D either, or 4D, or 5D, or 1000D. It's just embedded, it's jumping. But from these 2 principal components, you see that most transitions are smooth. That's all it can say, because visualization has only 2-dimensional convenience. And this is for the other motors. The other motors and color coded in another way, basically. And we tried planning for our neural networks. So it learned planning. So because planning is very extensive, we use simulation environment. So we did not use real world. In the future, we will use it, real world. So suppose that we start from here, then you have different settings for generalizations, and then you have different routes. For example, here, you have here. And once you figure it out, you literally get reinforcement learning, you get a reward. So it's reinforcement learning with select maintenance and rewards and punishment. Then we have different routes. We have landmarks. Those are the landmarks, visual landmarks. And we also let it learn the cost. The cost of navigation. The longer time you navigate, you more fatigue. Fatigue means punishment. And we also learn the distance. We count the number of steps it navigates through the cells. And we also learn the value. Value is learned through reinforcement. And we also learn it prediction. It learns called covert action and overt action. Covert means I think, I do rehearse in the motor space, but I do not really act. And then we also learn choose the action that has a better value. So instead of pick up the route that's longer, we pick up the route that's shorter, for example. So that's, if you're interested, you use how the network can do planning. Now that's probably surprising. Say, hey, neural network doing pattern recognition. No. Neural networks is living the word in doing abstraction. It learned the plans, it learned thinking, and learned choose the action and execute it, all right? And learning is autonomous in a sense of reinforcement learning. In fact, it also has a kind of, I would say, thinking-based learning, not just reinforcement learning, but it's like Emergent. If I'm doing this one, it's shorter, I get more reward. And I'm doing this one, I plan less reward, and I like that one. That's also implicit learned. All right, talk about Audition. And Audition, in this case, using the same network. So same network framework, but different data. All right, in this case is sound. All right, sound come here and 20 frames, 20 minutes a second is a frame. And you have Fourier sequences. And before we use dense label. We have really dense labels, and we do dynamic clustering, and we use the clustering as a label to supervise it. Now we have no labels, all right? And it's already submitted. That the silence, and this is the label, and this stage is label. And we do emergent, and we model the cochlea. MFCC is a male frequency capture coefficient, has been widely used for speech recognition as a feature. And we use cochlea learning model for natural sound, and not just speech, but including speech. And cochlea is a snake-like shape structure in the ear, and the base corresponding to high frequency. It's a band pass filter, more or less, with a response and a phase, actually. And there's a higher frequency and lower frequency, and the apex will vibrate slower, basically, will be sensitive more to the lower frequency. And we use a hair cell model, and has a pattern of image. The image is like cochlea, artificial cochlea. And the different location means phase information, and between the base and apex, it corresponds to band pass filters, basically, all right? And we also model the volume, and the volume in the sense that how high you hear and how much volume you generate to synthesis. And the next frame page will talk about the listening while speaking in real time on the fly. So suppose I have a waveform, right? And this waveform can generate by yourself. You talk, you hear. So density input, that's what you hear. That's artificial heard. Then we have a cochlea model. The cochlea model, we sense to this when they are motor, and we have a synthesizer that generate the muscle action from vocal tract. Then you can generate the driver speaker. The speaker will generate a model of the sound, right? So here you do synthesis, red synthesis, and in blue you hear, all right? So it's a dense tone. This becomes dense. Our action is dense, not label. It generates sound wave. It's dense. So dense action is available from synthesis. Then free of symbols. Before we have symbol, now we don't have symbol. And why we need to do that? We want to APFGP. We want to have dense muscles that generate very time-dense action to synthesize sound waves, not just label of the phoneme. And we learn the end, just like the framework we did before. So basically we have 20, 1 hour. This is frame, this is like 20 millisecond per frame. And this is wave coming in. And we delay a little bit because once you hear, if you want to say, it's like a simultaneous interpretation where we have delay a little bit, all right? So we delay a little bit, but net will learn the internal representation Y generate 5, the red circle means 5, 5, 5, then this is the muscle. This is a muscle model. We use the PCA. We PCA to generate muscle, the muscle synthesize, because PCA is good enough to generate muscle actions, and the projection on the PCA is the volume. And we generate some wave like that. And then we compare the sparse model versus dense model. That's a 1918 model. We found that with dense model, and that the areas are smaller. And then if we do concurrent, that's our latest model, 2020. It's, then you have blue is original, and red is synthesized. You see that it's not exactly the same, but we also have a human subject that test whether what here is the type that they intend to be. And we also did that in the paper. And subjectively, it's like what I said is not exactly the same as your voice, but we can recognize your voice and my voice as the same type. And this particular result show how the network grows actually. They start with a very small area. Then each neuron has a 3D location. So it's not just weight. Weight is like one solid dimensional space, right? But each neuron has a 3D location. We want to grow in a way so that the representation is smooth in the space, very much our brain, all right? And we grow the network of neuron near the 3D location of the neurons that match well, basically, all right? And each neuron has a 3D location and grow a smooth cortex and aim to simulate biological brain. And you can see that those are the brain. And originally, those neurons, red one are green ones, and will be over here, they are very close to each other. So this means that they are smooth. This is the original, they are close, electrons they are close too. So grow an auditory motor network that are smooth. Then during the embedding, as we said, in vision, now we have embedding in the temporal traces in the cochlear representation, and different color mean different phonemes. E, A, O, like that. All right. We did not pick out, we just pick a few neurons so that it's otherwise it's really dense. The next subject is natural language understanding. In this setting, we have not linked the audition with natural language synthesis yet. So we put that into two. Primarily is that in AI, the language part tend to be separated from audition. They are separate. We'll do that later to integrate both. So in this case, natural language input is word, but in order to simulate the cochlea, we match each word to a pattern, the pattern corresponding to the image in the cochlea. So learning two natural languages. Suppose we want to do language acquisition instead of language translation, because translation is not really biologically plausible from language text to text. We say we want to understand how baby learn the mother tongue, all right? So mother tongue have English and French. It's a bilingual environment. And we have 1,000 words learned and like 8,000 possible contexts, because if I say, hey, I don't have time, so each one corresponding to a context. Context is very important as a muscle output, and do not corresponding to the same, so this should be the same context. And in terms of French, je n'ai pas le temps, that in terms of meaning, they are corresponding to je n'ai pas, for example, these two should correspond to the same. So Q3 and Q3 are corresponding to the same. But in terms of language type, this is French, F, English, E. So we have two concepts in the motor area. One is the context, which is the meaning. Another is the language context. Language context has neutral, all right? Neutral is like before language started, it's neutral, all right? Then once you hear something that corresponds to a particular language, then it becomes a language context. So if we don't have noise, it's perfect, because we already proved that, right? You have enough neuron and you have perfect language acquisition. But with noise coming in, and the noise is not observed, then the neurons don't have enough, because input is new, and then we have like 0.02% errors. And this is a similar diagram. I want to show the similar diagram. In this case is the language. Then you have a pattern as a word and multiple neuron firing. Each pattern corresponding single word. And this is a concept about meaning and the language setting. Meaning and language setting. And then this is the context. Then the very dense. Then we have neuron firing and lead to the next language setting, context, and the language type. So X patterns of word, Z is the two concept zone, meaning of the context, and a certain context complete becomes a phoneme. The word or sentence, part of sentence, or the entire sentence. Then we have a language type, English, French, and neutral. And we supervise XZ because we learn the FA basically as a control of a Turing machine. And a hidden area Y grows to develop language net, basically a language net. Those are the neurons, hidden neurons. And the table about the errors, noise signal ratio, and if you have a signal noise ratio is high, you don't have any noise. But if it's low, 0 is like half energy is noise, half energy is the signal, then start to have that 5 dB is still very robust. 5 dB is very low noise ratio. I think that because the context will help you to fight noise. And to do prediction. Prediction is next word, all right? Next word is correct or not. And without noise, I did pretty well. For those who have unambiguous prediction, all right? Unambiguous transitions, then the predictions are really good. But with noise, start to degrade at the 0 dB. 0 dB, like signal noise, have the same amount of void energy. And that's embedding. Embedding, this case is the context. You see that the equivalent just that he has an equivalent means equivalence. And the I'm writing to her, and those are the context. And then the color corresponding to the labels. And the state has a lot, all right? And this is the color. And you can see that still more or less continuous. And that's another embedding type. Here is the 3 meanings. 3 long meanings that's corresponding to sentence. Those sentence, and that's embedding. And that's the language context. Language context, English, French, and neutral. And the color is according to the language context. Here, the color is according to the sentence context. So basically, it's very important to see that, all right? So each neuron has different roles, because each neuron in this case has a context ID. Here, each neuron has a sentence ID because participating in sentence. Here, each neuron has language ID, all right? Like FA has a top-down, each neuron has top-down and bottom-up input, and the top-down input tell you the meaning ID, bottom-up input tell you the hair cell or sound wave ID. The first class of the example, I like to give you the context of our product. There is a startup called Genesema, LLC, and you probably still remember Genesema. Genesema is the 8th property, grounded, emergent, natural, incremental, scout closed, attentive, motivated, abstractive. And this Genesema put together become the name of the startup called Genesema LLC. And the company has a first series of product as a consumer product and also good for professional as a APFGP platform. In this case, you have a camera. The camera has mounted on a cell phone, and there is a 3-object rack. The rack mounted with a camera, and I probably pull it up here. See that they have a stereo camera. That's a rack. Then you can put the cell phone in. Then you can mount also the viewer, the goggle. Goggle is mounted on the cell phone. Then it's portable. Why is it portable? Because you want to mobile. You want to mobile so that you take the baby out for work. So the controller is the sensor for your muscle, basically, and connected through wireless Bluetooth, all right? And that is the left eye, right eye. If you see, if another person with the same device, then you see, in this case, I don't know is doing training. The output of the network will be shown on the screen, so you can see. You also hear the beep. If it's close, we'll see. If it's far away, then he do. For the blind person, you cannot see it, right? So it's like a car with like sonar detector. So you'll be able to hear the sound to see whether I can navigate or I should turn. Oh, this don't do this. Here, do, and I can do this, like that. So we use the that's this year's work in this conference. If you're interested, I think it's the it will be presented at Friday, right? Friday. Friday 9:30 and a.m. and at 9:45 we'll have another paper. I will talk about the consciousness. Adam will talk about this work. So basically, we use the 2 eyes without really explicitly matching the left or right, and the camera will develop. The camera image will be used by the network to develop the correct receptive field at the correct weights, so that each neuron is the color tuned and disability tuned. It's a local receptive field, and then match the disability output in this case, all right? And we have a newer version coming out that will integrate molecular information, which is color, texture, and binocular information, which is probably disability and color and texture. And in this case, we have emerging neurons, and this will be shown by Adam. And there are, if you do disjoint test, different image frames, top down 0, right there. See that if you don't use context, it did pretty well, but if the context is too much, it's getting worse. It's like you cannot change your disability in the context, because disability may change over time, right? But if the disability in this case is 0.1, it's doing better. So basically, it's the amount of disability will really how much disability you trust. Last disability, basically. Last disability will help you to give a better prediction when the match is not perfect. The weight match with the current image. That image is new. You never seen that image, all right? If you're not sure, then the context may help you statistically, right? Because optimum in maximum likelihood. So you can see that slightly better. And this is number of frames. Number of frames you learn. And this number of frames is like 100 frames, 200 frames, and 700 frames. And at the beginning, and it did not do as well, but later on it did better, basically. The more experience, the better. Now, the next subject is an exciting subject called conscious AI and conscious machine learning. Now, many people talked about papers, also published paper about the consciousness, like Christopher Koch, he is one of the pioneers that studied attention and later on consciousness, but he is studying in a qualitative fashion in a neuroscience context, more intuitive. And our work is really holistic. And we need to resolve some 1 billion problems. I don't say it's 1 million. 1 million is not enough. 1 billion problems must be largely solved in order to say the heavy subject, C, consciousness. So we have a holistic solution. I overviewed so far over 2.5 hours already. It's a holistic solution to highly nonlinear problems. It's not just nonlinear, it's context-based, but even bottom-up is highly nonlinear. Right? Perception did not solve the highly nonlinear problem because perception did not do context, did not have a top-down. All right? And we have bottom-up, top-down. We have FA, we have a Turing machine, we have universal Turing machine framework. Okay, it's a highly nonlinear problem, and it was realized by DN clustering using neurons in a hidden neuron, and those hidden neurons are highly automatically self-organized using hidden learning. Although motor was used, but the motor was used as a part of input. It's not used as a supervised action or class label. No, it's not. So every neuron inside Y or inside the skull is unsupervised. Very different framework. I repeat again. Every neuron inside the skull, inside network, is unsupervised. So learning is a hidden learning. Using optimal hidden learning, what we call LCA. Then both supervised signal, if you talk about supervision output, is available through yourself. It's self-supervised or teacher-supervised at motor area via motor. And the bottom up is from images, from sound, or from the pattern of the word. So it's extremely highly linear solved without local minima. I repeat again, no local minima problem. You probably don't believe it. I'm not lying. So that's why you want to understand it. I'll get to how you can learn it. All right, I get all the convinced, all the proof are there. And no local minima problem, highly linear, no local minima problem. Why? It's optimal. Optimal means that no matter what kind of network you have, start with the initial guess, if you have the same experience, you get exactly the same solution. There's no, we know without using PSUTS, our network did not know the text data. No. Test data came in without knowing, and all the errors are recorded through lifetime. All right, using only one network. No multiple network with random initial guess. Every network with different random initial guess will reach the same network, same performance. So it's the only network after perception that does not use PSUTS, right? And it's a unification of the symbolic school and the connectionist school. And you probably recall in the 1950s, when I was a grad student at UIUC, Department of Computer Science, my advisor was in electrical engineering. I have two bosses, Naranja Hoja and Tom Swam. And I was really, really lucky in the sense that I got exposure of both computer science and electrical engineering. And there was a huge heated argument, debates on which is better, symbolic school and neural networks. And at that time, I was a student. I did not really look very closely, and I really did not quite understand it, because that's before I really got into vision. And that was during the early stage. And I become, even when I graduated, I did only doing motion estimation and structure estimation from image sequences. And I did not do anything about neural networks. The Perceptron first developmental network that I did. Later, many people used it without proper citation. In other words, I claim to plagiarize it. Perceptron was done after I got a PhD at that time. And I have a total freedom doing this one with the financial support from Naranja Hoja and Tom Swan, and whom I appreciate so much. The unification came out recently. Because symbolic school, we can understand it. Because based on DM, we understand the DM based on symbolic Turing machine and universal Turing machine. Huh? So it's not scruffy anymore. It's beautiful because we have a symbolic formulation. But a computation, it's not symbolic. No. Computation is based on connectionist model, which is neural network. Not traditional neural networks, all right? Not SOM, not CNN, and not LSTM, no. DM. Very different kind of network, right? It's a much better version than Perceptron. It's optimal, right? And it does not do convolution. And so the computation is connection school, but the understanding is symbolic. So it's like you get the best of the both words, the symbolic school word and connectionist school. They used to fight, they don't really talk to each other. And they attack each other actually. They just do their own way, That's why you have fragmentation. You have fragmentation in the symbolic school because different methods use different representation, handcrafted. And the connection school is slightly better, but different tasks have different network structure and they fight. Now, they converge, unified. So they should shake hands. Now we should learn how we can unify. Where do we unify? Where the platform we do unification? Here, the end. Sorry, there was a problem. All right, there was a technical problem. PPT, PowerPoint quit, and let's now we are back. So we have a unification of the two schools, and so the method that in terms of theoretical framework is very much in theory. It's theoretical in nature about consciousness. And the theory consists of Genevasa, Genesema, a universal Turing machine, and it talks about conscious learning. And the framework of DM is the same at the baby time and across later on the kindergarten time and adolescence time and adult time. So conscious learning takes place through the lifetime, throughout. So it's conscious learning that's really important. Not like consciousness is a product of learning. No, consciousnness or conscious learning is the causality too, all right? And then you should have a task non-specificity because you should not have a task-specific presentation. If you somebody talk about consciousness in the context text setting, he was only talking about the maybe explanation. He was not talking about the real computational machine that is capable of doing consciousness actually, all right? And it must use APFGP, and conscious AI is from conscious learning, and you need to unify natural intelligence and artificial intelligence, all right? Without the natural intelligence model, motivation, and it's impossible for DN to reach this point, right? So it's a unification, not just within the AI, not just the developmental AI, or not just the symbolic AI and connection to AI, but also unification between the natural intelligence and artificial intelligence. That's kind of exciting, all right? So then what do you mean by consciousness? And consciousness must be starting from day one, all right? Day one, even before birth actually, all right? So you need the developmental learning and day one after birth too. And the baby consciousness to adult consciousness. And degree of baby, the consciousness is more primitive, simpler, and for adult it's more mature and more sophisticated. And but a minimal set to boost the degree of consciousness is 1. Right? Give an example. Suppose this is a this is the left eye of the stereo video I took in New Delhi, India. That was the end of last year, and that was a very popular street, and around the train station, New Delhi train station, and I saw that horse. There are many horses actually. Also cattle, and they are just freely navigating, and I don't even see an owner. I don't know whether the owner is following me or not, but I was following this one for about maybe 15 minutes, you know, and I did just walk very long. And if there's traffic, he will stop. And but he did not really go into other places. He did not just block the traffic. No, he didn't. And this is a human, and human and animals just navigate by manipulating around in the hustle bustle street of New Delhi, right? And so the issue is that they do attention to number, right? They have a task in mind, and this I don't even remember. I think that's a cattle. That cattle have a task in his mind, all right? And the paper, this diagram was in that paper. The conscious intelligence requires autonomous programming for general purposes. That's I submitted to Science, it was rejected, and I submitted to Nature, it was rejected, and then I submitted AIXIV in June. Then I really thank ICDL conference, EpiRob, that allow me to have a publication over here. Conscious intelligence require developmental. I added developmental here. Autonomous programming for general purposes. That will be Friday, October the 23rd. And I told you the time, I think I did, 9:45 a.m., all right? And after the 3D talk by Arden No, and it's a very short 15-minute talk, so so probably you get a precursor of the talk over here. And I do not present everything here, just give a snapshot. So basically, symbolic school is no way to the consciousness, right? Because it's symbol. When symbol is put in there, all right, like stroke, or vertical bar, those kind of symbols, once you put it there, a machine has no idea what that means, no idea what the horizontal bar means, and why do we have to this one treated the same, right? Why is this vertical line or tilted line was treated the same? He had no idea because he did not know the stroke. All right. For machine, you really need to say that, all right, this one's first, and at that time you don't want to call it horizontal because baby did not know the horizontal, and the kindergarten kid did not know horizontal. You just do it, all right? Just do it. Maybe hold her hand. And just do it. That's E. E is done. He did not understand what E is actually. E will be later on used, all right? Like this is the lower case of E. That's later. So skill is accumulated over lifetime. So don't handcraft any symbol into the brain, all right? And this is connectionist, all right? So connection in this case, it's not for C either, because it's a bottom up only, all right? It did not use context, right? So it's still bottom up. There are competition in there, I understand, but within the same network, like for example, that he did have some denominator composition, basically reweighting. But it's a still pattern recognition. Connectionist school for pattern recognition is not for consciousness, see. But Genesema is an important part of the mechanism that are all necessary for C. Give example, if you are not grounded and AlphaGo is not grounded, so it's not for C. AlphaGo is not for consciousness, so it must be a real robot. Emergent. Hand programming is not. But human must be in the loop because hand programming is not in the loop of symbolic design. So you cannot use symbol, you must do emergent. So once you do emergent, human had no idea of what the pattern is, just too messy. But statistics, heap learning will take over automatically, all right? And a human can understand in term logic, like UTM, right? Must be natural, all right? IBM Watson for Jeopardy game is not for consciousness because symbol require human to design what do you mean by features, right? What do you mean by yes, right? What do you mean by no? What do you mean by the choice? Must be incremental, all right? And if you do ImageNet, like batch training, it's still pattern recognition. It's not sensory motor recursive, I said. You will not get the image if you don't have an action. So don't ask people to collect the data from the internet. No, no. You must ask the robot to collect the sensory input on its own, just like cattle in the previous video, or the human. Skull must be closed. All traditional neural networks are not closed. SOM, SVM, CNN, ASTM. Must be attentive. The attention must be autonomous. All right? All traditional neural networks are not. Must be motivated. And just function approximation is not. Many reinforced learning neural network, they also doing functional approximation. They are not for consciousness. Abstract. You must be able to abstract rules based on motivation, based on computation, based on interaction with the physical world. Just functional approximation are not, like SOM, SVM, CNN, AOSTN, and the recursive neural network, RNN, and so on. So another thing is that C must go through development. C is not the thing that somebody programmed, or C is not thing that for the oldest person. No, C is everywhere through the life of a person, through lifelong APFGP. The FGP mark takes place from earlier time as soon as the life is incepted, right? So conscious learning is the key. Consciousness is not a thing of programming. It's not a thing of capability from learning either, say supervised learning or reinforced learning. No, consciousness is through conscious learning through conscious action, and the learning must be conscious. For example, if the tree is useless for me, and I'm not a painter for drawing tree, I will not pay attention to the tree leaves, right? Maybe a biologist who is supposed to do teaching drawing the how to draw trees, maybe he should pay attention to, but I barely pay attention to that. So that's why consciousness is must related to the conscious actions. So it's not just the outcome at the last day of the life, but also causality of the consciousness of learning of conscious skills through lifetime. So the life must be autonomous first. The inside the brain must be totally automatic. And nobody should get into the brain. Then how do you learn this kind of beautiful, you probably don't trust me, Juyang is making a scam. But if you believe that, then probably we already have a Brain Mind Institute that was starting from early on. I think maybe 2012, right? And from 2016, we have a contest. And each year we have courses. And the 831 is cognitive science for brain mind research and start from 13. And 861s for automata theory combined with the motivation of brain studies start from 15. And 871, it's a material, it's a covered material using a book that I wrote. Now you have a second edition. Use that as test book, Computational Introduction to Brain Mind Model, and stuff from 2012. And each course include video lectures, PowerPoint slides. There are 3 exams. Also, the instructor will grade it for you. And if you pass, it will be a BMI course certificate that you can, maybe you can list that in your resume. And 2016, we have AIMA contest. I think that if I'm wrong, let me know. The AILM contest is the first one because people in machine learning really did not, it's not generally purpose enough as a scope AI. So we have AI and machine learning put together. It's unique in the sense that the must be task independent and it must be modality independent. All the the content must go through the setting. You don't even know what kind of meaning you have. And it does have a, you know, that's a modality. You have a modality, you have a vision, audition, and a natural language, right? And a full-time student, if you're a full-time student, you get a tuition for waiver, or you need to pay for administration fees, basic application fees. For 150, you have all three BMI courses, and you can have entry in the workshop that coach you how to do a context, and you also have interface. You have availability of the engine, DN engine. And if you like to introduce other engine, you can also participate using other engines. That's okay, but it has to be incremental. Has to be task non-specific, and also we need to limit the number of neurons you have. So it's the same number of neurons, look at the performance. All right, it's a limited resource, and you can also have with $150, you have one content entry as a team. All right. And the startup, Genesema LLC, provide hardware and software for APFGP for users, contestants to use. And maybe also can be for other people that like to start business. And the learner version, which is the developer version, and the VCML 100. And that's about slightly under $1,000. But you have also other software and developers service. Then the performer version, it's a 50 version and a 40 version. That PMP, I think the machine performance, I had errors. This is MP and MPR. That this is about slightly in the 500 and slightly in the 400, but without this one without goggle, right? And this one without learning software. Autonomous programming operating system, AOS. That's a supplied. That's operating system sitting on top of the conventional operating system, so that it allows you to do auto programming. And 3D Tube is a social network for 3D contents, and you can use the studio camera to take video, and you can post it on the 3D Tube to share with your friends and communities. 3DI is a developmental vision system with Audition and a goggle and visualization for doing machine learning for APFGP. In conclusion, I'm almost done. The 3 hours almost there. APFGP is mathematically proven and using constructive method. And it's at the end and proved that it does APFGP. And early experiments, including 3 bottleneck problem AI, vision, audition, and natural language. And the DN can learn Genesema UTM. It's a general purpose and a fully automatic inside the skull through the lifetime. And neural network community is in a alleged PSUTS. So it's a kind of crisis if you believe that. But it may take some time to overcome this crisis, because many people would not really, they read papers, read our papers, but they on the surface, they ignore it. Maybe it takes many years, just like perception, before they start to caught up, was caught on and start to be used widely. And natural intelligence and artificial intelligence have been unified by the APFGP theory here. And conscious machine learning will arrive through machine learning, not through task-specific programming, but through not just machine learning, through conscious learning. All right, remember the term, take-home message, conscious learning. Then it will arrive and become very powerful, and hopefully can reach animal level performance. I don't know how soon, how many years can reach human level performance, and I doubt that will reach human performance during my lifetime because I'm old. You guys probably have more years to enjoy. Thank you very much. If you have a question, you can write comments. I will submit this video to ICDL-EpiRob conference, and I will make it public available. So most likely it will be available on the YouTube and also on the 3D Tube site, 3dtube.org. Thank you very much.